Hi there, this is Mr. Schnitzius again, and I'm one of the A Squared I geometry teachers here today to talk to you about activity 6-1. Today we're learning about justifying statements. So this activity is the beginning of working with proofs, specifically a certain type of proof called a two-column proof. So we're going to use definitions, properties, and theorems in order to justify a statement. So definitions, that's something as basic as an angle is a right angle if and only if it measures 90 degrees. We're going to look at several different properties in this activity. We've already talked about how we can use deductive reasoning to turn a conjecture into a theorem by proving with deductive reasoning that that theorem is true. And when we say to justify a statement, that means explaining how we know a certain statement is true. You don't want to just make a claim and not be able to back it up. If you make a claim, you need to be able to justify or explain how you know that statement is true. Just like if you're a defense lawyer, if you make the claim, my defendant is not guilty, but you don't give the jury any reason to believe that, then your client is going to be really, really unhappy with you. We're also going to write two-column proofs to prove theorems about lines and angles. So this first lesson, this first video is kind of warming us up to getting to writing two-column proofs. We're just going to talk about using properties, postulates, and definitions to justify statements. We're going to talk about some ways that you can justify statements and also talk about some helpful hints for writing a two-column proof. So these are some outside notes outside of your ebook or the PDFs. You might want to jot down some of these tips, and this also refers back to some of the terms that we've seen before. So geometry is an axiomatic system. Axiomatic system means that from building blocks, just like a building is built with the first floor first, and then you lay a good foundation for the second floor, and then the first and second foundation form a foundation for the third floor. Geometry is built the same way. From a small basic set of agreed upon assumptions and premises, we can get an entire structure of logic that builds up everything that we know about in geometry. The axiomatic system of geometry was actually the name of your activity 3, so you've already seen how axiomatic systems work a little bit. And we have already studied some of these fundamental terms. Those would be the undefined terms in geometry that you learned about in activity 1. Do you remember what those are? Those are the point, the line, and the plane. So it turns out that any term that we use in geometry can in some way be boiled down to either one of these three terms or a combination of those three terms: a point, line, and a plane. So deductive reasoning rather than inductive reasoning is going to be more important whenever you're writing a proof. A proof is an argument, a justification, or a reason that something is true. When writing a proof, you can organize the steps and reasons used into two columns. So we'll get some practice with that in the next video. Right now, we're just going to talk about ways that you can justify, that you can show that statements are true. Here are some tips for writing two-column proofs. This is a good problem-solving strategy, not just for proofs, but for any type of problem. If you don't have a picture, draw the picture, but also label the picture. Include all the information that you know about and put it in the picture. Write down your given and proof statements. A given statement is what starts a proof, and a proof statement is the statement that you're trying to prove, the statement that you're trying to justify as true. Analyze the information first and come up with a plan for your proof. That's just kind of getting an idea of where you're going in the proof and how you're going to get there. So this is one of the big points for this first video. You must have a reason for every statement. And each reason, besides given, should be either a definition, a postulate. In activity 4, I believe, you saw some different postulates like the angle addition postulate and the segment addition postulate. That's a statement that's so basic that we can accept it without proof. A property, like we're going to look at in a second, or a previously proven theorem. So these are your ways that you can justify that a statement is true. Every time you put a statement in a proof, you don't want to just write down something that you think is true. You want to write down something that you know is true, and you want to give a reason for how you know that is true. You also want to use symbols and abbreviations for words within proofs. Sorry, that should be number 5, not number 6. A good way to do that would be to use the congruent symbol if you're saying the two angles are congruent to each other. And lastly, you want to reread your proof when you're finished in order to ensure that it makes sense. So since we said that there are some properties that you're going to want to know, we're going to look at some properties that are going to come up fairly often whenever we're doing two-column proofs. Now, most of the proofs that we're going to do in this class are going to be geometric proofs in activity 6-2. But even in geometric proofs, we still need some properties of algebra. We saw when we were doing using deductive reasoning in activity 2, we saw that when we were proving using deductive reasoning that a certain equation had a solution, we could justify a step in working out that equation by citing the addition property of equality. This basically says if you add the same number to both sides of an equation, you don't change the value of the equation. So just like there's an addition property of equality, there's a property of equality for all 4 basic mathematical operations. The subtraction property of equality says the same thing. If you have A equals B, if you subtract the same number on both sides of the equation, then you keep the equation balanced. The equation still equals the same thing. Similarly, there's a multiplication property of equality. If A equals B, then if you multiply both the left and the right side of that equation by the same number, then the left side still equals the right side. And we've got addition, subtraction, multiplication, and then of course division. If A equals B, if this equation is true, then if you divide A and B by the same number, then the equation is still balanced. The only tricky thing about this one, though, is C cannot equal 0. You're never allowed to divide by 0. So these are pretty basic. There's nothing really surprising about these. Over here, there's some properties that we use a lot that you might not have thought about the name of. The distributive property, I'm sure that you remember this from Algebra 1 class. This says if you multiply A outside the parentheses, you need to multiply A times B, and you also need to multiply A times C. The reflexive property, that says that a number is equal to itself. This one won't be used very much with numbers, but whenever we have a line segment that's part of 2 triangles, the same line segment in both triangles, then we might use the reflexive property to say this line segment is the same in this triangle as it is in this triangle. A nice way to remember this is, I know in language classes, especially in Spanish class, you have reflexive verbs that refer back to yourself. So if you have the verb for washing your hands, you wouldn't just say lavo los manos. You would say me lavo los manos. I wash my hands. So if something's reflexive, it's referring back to itself. You could use the reflexive property to say that you are congruent to yourself. That's kind of a mind-bending statement. The symmetric property says that if A equals B, then we can switch the order and still get a true statement, then B equals A. This is a really, really big one. I'm going to star this. Transitive property says that if A equals B and B equals C, then A equals C. So when I'm teaching this in the school year, I'll usually take some people in class whose names start with these letters. So I'm just making up names here. Let's say that Albert is as tall as Beatrice, and Beatrice is as tall as Charlie. Well, then who's taller, Albert or Charlie? Well, it kind of logically makes sense that if they're both the same height as Beatrice, then they have to be the same height as each other. And so that's all the transitive property is saying. It's very logical, it makes sense, but there's a specific name that I'm also going to highlight because we're going to use this property a lot in proofs. And another property that we're going to use fairly often is the substitution property. Just like your algebra teacher showed you that if one quantity equals another quantity, you can substitute those quantities in for each other. Same thing happens a lot in geometric proofs. If A equals B, then A can be substituted for B into any equation or any inequality. So we're going to use these properties to write out and fill in the blanks on some 2-column proofs in the next video for activity 6-2. Thank you guys.